Hi everybody, welcome back. We're going to cover waves today. I've heard you guys are doing a really good job, and so keep up the good work. I'm really proud of you guys, so keep going. We're covering waves, so if you think about the wave in front of you right now, we have a water wave, and we discuss waves in terms of what medium they're traveling through. So a medium is like a material. So if you think of like an artist working in the medium of oil or acrylic or watercolor or something like that, that's the material that's being used. So in a wave, the material is called the medium. Yeah. So we're going to talk about the different mediums that waves can travel through. This particular medium is obviously water. So a little different version of a wave is when you have a wave traveling through a wire, an electromagnetic wave traveling through a wire, sending the signal up to the speakers, right? It's going to the speakers, and then it's recreating this signal and pushing air and creating that wave in air. So there's two different waves here. We can see beyond the water wave, right? We see that we also have electromagnetic waves, and we also have air waves, or different compression amounts in the air that travel through the air, and then it strikes his eardrum, right? And then he can hear it. Interesting. So now we're going to go a little further into some of the math of it. Not a lot. It's really easy math. If you could get your... And we're also going to take some notes on some vocabulary. So definitely get out your notebook and your calculator and a pencil. First off, we're going to define a few terms. The amplitude is this height right here, from the equilibrium point to the top up here. We call this the amplitude of the wave. And this is from the equilibrium point, which is in the middle of the wave, or where the wave is not disturbed. Let's take a look at that. If you have a water wave, or just some water without a wave yet, and you drop some water, a water droplet into it, it would start to propagate this wave out, right? And before it propagated, this level of water was nice and smooth out here, right? So that would be your equilibrium. And then after this wave propagates and comes back to rest, that would go back to the same water level. That would be the equilibrium. So when we look at this line here, the equilibrium line, that's what we're thinking about, the undisturbed level. Okay, so there's a couple of different ways we can define some parts on this wave. So we're going to start with just looking at this wave with respect to time, because this is like a vibration graph, a history vibration graph, and we're just looking at the time it takes for the wave to travel. So you're plotting time on the x-axis, and you're plotting the disturbance, the magnitude of the disturbance, the amplitude, on the y-axis here, right? So we'll call this the y-axis, and we'll call this the x-axis, and this is with respect to time in seconds. The other thing we want to look at is this is the peak point up here is called the crest. So you want to make sure that's in your notes. So all of these points right here at the top, these points would be considered the crest. And the points down at the bottom, these are the trough. Down here we have the trough. So the lower points are the trough, and then the upper points are the crest. So make sure that's in your notes as well. The distance or time that it takes, not physical distance, but the time that it takes on this graph, let's do purple. The time that it takes on this graph to go from one crest point to another crest point, that would be called the period. And the trough, same thing. If it went from one trough to another, it would be the same period. You can see these distances are equal. Another equal distance would be from this point here to this point over here. Again, that's a full cycle. So we've already talked about periods before when you talked about Earth, and we had the moon, and it was traveling around the Earth, and it took one period. That was a period for it to go around one time, right? So it's how much time it took for it to go around one time. That's the period. So period, again, is measured in seconds. That's the SI unit, seconds. And a wave has the same exact thing as we did with Earth and the Moon, right? We have T for the period, and that's the period of time it takes to go around. In this case, it's the period, the time that it takes for the wave to make one complete cycle. So you want, wherever you start the cycle, you have to end the cycle back. So that's a complete cycle then. Because you could do the same thing here. You could say, here's my starting point on the circle, and it went around. You get the idea. You have to go around one complete time. So same thing with a wave. Wherever you pick for your starting point, you've got to go one complete cycle to the next one. There's another way we can look at waves. We can look at the wavelength. Wavelength is measured in meters. So this is a new graph that is not measuring time anymore. We're actually measuring the meters of travel. Okay? So that's a physical distance you're measuring in meters. We refer to that as lambda. That's not sheepda, that's lambda. Okay? So lambda is this symbol we use for wavelength. And we're going to go ahead and try and solve a problem of what if this little guy was riding this wave out in the ocean and he went from this point to this point. Could we figure out how fast he's traveling? So what would be the velocity of the wave? Well, the velocity of the wave should be the velocity that that little guy on top of the wave is actually traveling, right? And that would be distance over time, because we know that velocity is equal to distance over time. Well, the distance over the time in this case is the wavelength, right? Because he traveled this wavelength. And the amount of time that it took him to travel that wavelength is called the period. Interesting. So now down here we have the wavelength divided by the period. That would give you meters over seconds. Very good. Let's see if we can work a problem like that. We have, let's say we're given that the wavelength here is 6 meters and the period is 2 seconds. Well, we should be able to calculate that, right? Because we would just put the wavelength on top, 6 meters, divided by 2 seconds, and real simple, we get 3 meters per second. So we know that this guy, he's on top of the wave, he's actually traveling in this direction. I shouldn't point to the guy in that direction. He's traveling to the right. So it's a vector, right? We can say he's traveling to the right at 3 meters per second. Great. So now you know how to solve for the velocity with respect to a period. What if we talk about frequency? I don't know how much you guys have heard about frequency. I'm sure you've heard the term before, but let's discuss what frequency is. So frequency is the amount of cycles over time, right? So the units we use is 1 because we don't use the cycle as a unit of itself. It's just what's taking place. So a whole cycle is taking place over seconds. So it's 1 over seconds. So hertz is how we measure it in the SI units, but hertz is literally just the same thing as 1 over a second. So let's take a look at the equation for solving for velocity when you know the hertz or the frequency. So we already know that if you have lambda over the period, that'll give you velocity. What if we have lambda times the frequency? Well, wouldn't that be meters times 1 over seconds, which would still end up giving you meters per second? So we could see that this is literally the same thing. It's just the inverse because the period is the inverse of the frequency. Okay, so basically we just multiply, with this new problem, we multiply the wavelength times the frequency. And we get 6 meters times 0.5 hertz, and surprise, surprise, it's the same answer. He's still traveling at 3 meters per second because I happen to pick 1/2, which is the inverse of the period, which was 2 seconds, right? So because I picked 1/2, it ended up coming out with the same answer. So that's a really simple problem. you guys are probably going to be solving some problems similar to that. You might also be solving some problems where they're asking you to look at wavelengths. And sometimes it can get confusing, so you really kind of want to show you the different wavelengths, which is the same as the period. There's a wavelength from here to here. So it's starting here at this point, and it's ending at that point. So it's on a full complete cycle. And you can also measure wavelength from the crest to the crest, and you can also measure wavelength from the trough to the trough. Okay, now if I put different points on here and I said, oh, there's A and here's B, how many wavelengths is it from A to B? Well, you'd go 1 and then a half, right? You didn't go all the way back, so it's 1 and a half coming back to here. So just something to keep in mind when you're calculating stuff. They might ask about different points on a line. So I just want to review with you that waves travel through a medium. And that medium can be a gas, liquid, or even a solid. And there's two different kinds of waves. There's transverse waves and longitudinal waves. Both of these I think you're going to get introduced to in your lab. So I want you to keep in mind that there are two different kinds of waves and pay close attention when you're working through your lab and learn the difference between a transverse wave and a longitudinal wave. So have a great day, guys. I'll talk to you later.